So as is the case, I will make the lecture available via the class web page on YouTube. So let's see, where is the slides here? So hopefully everybody can see the slides. Are the slides visible to all?
Yes, sir, they
Yes,
are.
sir.
Okay.
Yes,
Okay.
sir.
Okay. So let's start the first topic. The topic is memory errors. In particular, a special class of memory errors called buffer overflows. And in this particular class, we'll actually be focusing mostly on what is called stack-based buffer overflows. I will talk briefly towards the end for about what are called heap-based buffer overflows also. And also we'll be talking about defenses. So what I will do is I will tell you about how these attacks work, give you a broad overview of the defenses, and then talk about 5 or 6 specific defense technologies in much more detail. And that's what it's going to cover pretty much the entire month of October. So for this particular portion of the course, there are virtual machines that are available on the class webpage. You can go and download the virtual machine images. To run them, you will need to download Oracle VM VirtualBox. So with VirtualBox, you can actually start the virtual machines and play around with it. So there are 2 virtual machine images, one of which is for the stuff that we are doing in class. I will try to do a live demo so that we'll be able to get a feel for the actual code. But there is also another virtual machine that is there for your first homework. So I think I can switch off the camera because it will consume bandwidth otherwise. Okay, all right. Okay, so what we'll do, let's start off with buffer overflows. And the first part of the course is going to be about exploiting buffer overflow vulnerabilities. So the reading for this is a paper called Smashing the Stack for Fun and Profit by Aleph1. Obviously, it's not a real name, it's an assumed identity. And this was published in a magazine called Frank Magazine. Unfortunately, the magazine is being discontinued. It's no longer in publication. But this used to be a hacker magazine, right? And this was published back in 1996. So it's not a scientific paper in the traditional sense of the word, but it gives you a hacker's perspective of how to go about doing things. So just to give some idea, some historical context, buffer overflows have been around for as long as computers have existed and for as long as the C programming language has existed. So people knew even back in the 70s and the 80s how to go about exploiting buffer overflows. And, in fact, these are buffer overflow exploits were among the most widely exploited class of vulnerabilities, including the very first computer worm, which is called the Morris worm, back in 1988. Okay, but they remained sort of a dark art that was known only to a few people until this paper came along. Okay, so this paper essentially took this dark art that was known to a few people and made it a precise science. Okay, so in some sense, you can think about this particular paper as being a cookbook for how to create buffer overflow exploits. So if you read it, you will know how to create a buffer overflow exploit pretty much at the end of your reading of this paper. And in fact, all of you in the first homework, you will essentially be doing pretty much what is in that paper. You will learn how to create buffer overflow exploits. Of course, things have gotten slightly harder in the modern day because of various defenses that have been deployed, and we'll also talk about that during the course. Right? What is it? What is it precisely that has made these exploits slightly harder? It's not impossible, but it's slightly harder. Okay, so we'll start off with exploiting buffer overflow vulnerabilities. So naturally, this is the material over here is going to be black hat in nature. In other words, it is going to be offensive in nature, offensive security. But and the question might arise: why are we learning this? The tricks of the trade of the attacker over here, right? Am I teaching you to become bad guys? And the answer is no, right? So every security course must cover both black hat as well as white hat techniques. So over here, we are going to be covering the black hat techniques, which means that you will learn how to exploit things. Now, this is not to say that you should take your newfound knowledge and go and try out these attacks on the internet. you will get into serious trouble for doing so. So please consider this a disclaimer that what I'm teaching you only for the purposes of understanding how attackers work. As a security person, it's always very important to understand how attackers work, because otherwise, how you design your defenses, right? We need to learn to think about security both from the perspective of an attacker as well as from the perspective of the defender. So that's why we are covering this. And this will be a recurring theme in this course. We'll always think about attacks and defenses and attacks and defenses and so on. Okay. So that's what makes the field dynamic. That's what makes the field exciting. Okay, so what is a buffer overflow? Well, this picture here shows you like what a physical buffer overflow is, right? If you fill water in a dam beyond its capacity, at some point in time, the water is going to have to come out from the side of the dam, spoiling the entire countryside. Okay, that's exactly what a buffer overflow is, but more in the cyber world, right? So you have some buffer space. In this particular case, the reservoir to hold some resources. But you end up storing more water in the reservoir than there is space. Naturally, it ends up causing damage. So the question is that we have to answer in our setting is, what is a buffer in a computer program? The short answer is that it is an array, right? Either an array that you allocate on the stack as a local variable by asking for space, or it can be an array that you allocate in the heap using a malloc call. Okay, and so the main goal over here will be to try to understand what sort of damage a buffer overflow can do. Okay, so it's a kind of programming error that happens in C and C++ programs or any other memory unsafe program. I should mention that Java is immune to these kinds of buffer overflow attacks because what happens if you try to write into an array, let's say you ask for an array of size 8, okay, and you write more into this array than 8 bytes. What happens in Java? Any sort of ideas? Anybody wants to chime in? So what happens? You can raise your hand and answer.
In Java, there are dynamic arrays. If the size of the array is exceeded, its size will double. Automatically, the array size will get.
Not the basic arrays that I'm talking about, right? I mean, of course, there are, in JavaScript, for example, you write and then it sort of grows. If you ask for an array of size 8, right? I mean, I'm talking about the traditional vanilla array that you sort of read in the first few chapters of Java textbook. What happens if you write more to it than there is space in it? What is the protection mechanism that's sort of built into Java? Nobody knows.
An exception will work.
What? Please go ahead.
An exception will occur in the Java programming language because there will be length bound checks.
Yeah, so you get array out of bound exception, right? That's sort of the built-in check over here that Java has, and the reason that Java can provide this is because Java has a runtime, right? It has a Java virtual machine that's sort of tracking what's going on, and whenever you try to write more into this array than there is space, you will get an exception. So that's the built-in security mechanism that Java has. But C and C++ don't have these kinds of runtime, right? So you allocated some space in the memory to store some data, but you wrote more data into the buffer than there is space to accommodate it. So what I will show you is using this simple programming error, you can actually launch very devastating security attacks. And I will tell you briefly, what exactly I mean by these kinds of security attacks, what the attacker is capable of doing. Okay, so these buffer overflow vulnerabilities, they have a really long history and they have resulted in numerous high-profile exploit incidents, right? The Morris worm from 1988, it is the first ever recorded computer worm, and it exploited a buffer overflow vulnerability in the finger daemon, okay? And it was written by who? It was written by, naturally, Morris, right? So it's a little bit interesting to go and see who this Morris was. And so this Morris, and here, so I hope everybody can see my browser. So this Morris is at the point that he wrote this exploit. He was a graduate student, a PhD student at Cornell, doing computer networking research. And apparently the stated purpose of him doing this buffer overflow exploit was to measure the size of the internet. He had a certain way of picking machines, and he wanted to measure the size of the known internet at that point. Remember, this is 1988. So he got into deep trouble because at that point he brought down a significant fraction of the machines that were part of the internet at that point. So he went to jail for a couple of years, but then he got out, and then he did well for himself, right? I mean, so here he is, and you can actually see that he is a faculty member right now at MIT. Okay, so this used to be possible. It's no longer possible. Of course, if you do something like this today, you will not end up like this. You will probably end up in jail. Okay, so this is, although it's an inspiring story, don't get inspired. Okay, but that's Morris, right? I mean, so there is an interesting anecdote behind like the first uh, really widespread computer worm. Code Red back in 2001. There is the Sasser worm back in 2004. And the reason I know about Sasser worm, it actually launched in August 2004. And I remember this because of a very unique incident that happened to me, an anecdote that happened. So I bought my very first laptop in 2004, August 2004. It was Windows XP, right? And it was an HP laptop. I went and bought it. And it so happened that I just opened it up, and the first thing that you do is you have to register the laptop with HP. That's the screen that pops up. And it, as luck would have it, I opened up the laptop and I connected it to the internet at precisely the right time, that exact time that the Sasser worm was just released. And the Sasser worm was actually targeting a vulnerability, a buffer overflow vulnerability on IIS, which is the web server in Windows XP that used to be turned on by default. And so the first thing that happened to me when I bought my first laptop and just switched it on and opened it up and connected to the internet was that I got hacked. Okay, so and then of course, I had to go patch it. There was Windows XP Service Pack 2 that was released, but it's kind of ironic. And now when it happened to me, I got shocked. I was just beginning to work in security and I had no idea what had happened. But all things happen for a reason, and now I can use it as an anecdote to tell you how I got started in computer security. It's always an interesting anecdote to tell you. Okay, so that was the Sasser worm. And there have been numerous high-profile events in the intervening years. The most recent, probably high-profile vulnerability was what was called Heartbleed back in 2014. There must be many more after 2014. I've stopped keeping track, but Heartbleed was a buffer overflow vulnerability. Well, it was a buffer overread vulnerability in SSL or TLS, which is the software that you use for encryption. Okay, so that's why embed TLS, and we are talking about Rust and so on for our project. It using Heartbleed, using an exploit against Heartbleed, you could actually read encryption keys that were stored in memory. Okay, so I've been using these terms rather interchangeably all this while, vulnerability and exploit. Let's sort of get these terms very clear in our head. What's a vulnerability and what's an exploit? Any ideas? Please, somebody chime in.
So a vulnerability is like the problem that exists in the program, and I guess exploit is making use of that problem in the program and I guess gaining access or like somehow exploiting that problem in the program.
Right. So vulnerability is just a programming error, right? For example, this buffer overflow vulnerability, it's an error, it's a programming error. An exploit is a concrete sequence of steps that you use to take advantages, vulnerability, and achieve some concrete goal as a bad guy. Okay. So what is this concrete goal that you want to achieve is what I will explain in the next few slides. So I will get there, but let's look at a benign example of a buffer overflow vulnerability. So here's a program. It's a C program. It's a C function. In fact, foo, it's just asking for a local buffer of size 8. So it's a character buffer. It's allocated on the stack, the activation record stack, and you are doing a stir copy, which is a library call, a standard C library call, and the notation here is destination comes first, source comes second, and you're writing hello world into this buffer. Okay, it's a rather benign vulnerability. It's not exploitable, but it is a buffer overflow nevertheless. And the reason is because you're writing more bytes into this buffer than you actually allocated space for. So you asked for 8 bytes. Maybe the compiler actually gives you 8 bytes. We will see that the compiler can give you more, but the compiler, let's say, has given you 8 bytes. But how many bytes did you end up writing? Well, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and there is a \0 at the end, 12 bytes. Okay, so you wrote 12 bytes into this buffer, so it's a buffer overflow vulnerability. And what can happen is that if there is some other data that is stored on the stack right next to this buffer, you might end up overwriting that data or corrupting that data. That's the worst that can happen here. That's why I call this a benign buffer overflow vulnerability. Okay, so it's not exploitable. You're writing a constant string into the buffer, and probably nothing will go wrong. Maybe your program will crash, or it will see corrupted values. So here is an example of a malicious buffer overflow vulnerability. Okay, so in the sense that you can actually do bad things with this. So what does this program do? Well, at this point, you've got this get user input. It's a program that takes no arguments, and it's allocating a stack buffer of 1024 bytes. Okay, there's a getS call, right? getS is a library, standard C library call that just takes user input from the command line and it writes it to this buffer. Okay, so as you can see over here, this simple programming snippet is just taking stuff from the command line. In fact, it will take stuff in the command line until it sees not a \0, but rather a carriage return, which is you press an enter and it keeps reading and then it fills it to this buffer. So if you're a bad guy and you want to make this program crash, you can just feed it like a really, really, really long string and you can observe its behavior. In fact, I encourage you to go and do this on your machine and see what happens. Your program is going to terminate with a segmentation fault. Okay. Now that seems rather benign, right? I mean, hey, it crashed, big deal. And if you're running like a really critical program that has this programming pattern in it, it may crash. But hey, what's the big deal? Maybe it just crashed. What else can it do? So what I will show you is that this particular vulnerability and the exploits against it can actually be used to take over this program, not crash it, but rather gain the privileges of this particular program. Okay, which means that the attacker can do everything that this particular program can do. Okay, that's going to be our sort of goal in this in the process of developing these exploits. Okay, so yeah, so what can buffer overflows do? Buffer overflow exploits do? Well, they can be used to trash memory, which is corrupt memory. You can crash the program, the segmentation fault. You can use to hijack the program, okay, which is spawn a shell or execute code with privileges of the program. In fact, we will actually show you how to spawn a shell. So why is this relevant? Well, the reason this is relevant is that every program on your machine, it actually runs as a process, right? The way that your operating system manages security or it thinks about resource allocation for every process is that it assigns every process an identity. What is the identity attached to a process? Well, it is the identity of the user that started the process. So if my username is Alice and I start a particular process, then that process is going to be endowed with all of the privileges of Alice, which means that it can read and write any files on Alice's file system, and it basically has access to everything that Alice can do. If Alice can open a port on the machine, then so can this process. Okay, so that's the idea behind how processes are managed on a machine and how the operating system actually gives processes to privileges to processes. Okay, so if you can hijack a particular program, then essentially you have the privileges of everything that the program can do, which means that now that particular program, which is listening to the attacker, can do everything that Alice can do. Okay. Now, why is this dangerous even, right? Where is this attacker sitting? Well, if the attacker is just somebody who's entering stuff on the command line, Not a big deal, right? So now Alice, who is this person sitting and interacting with the program, will have to let this other person enter a really long command line, right? That doesn't seem very bad, right? And it's an exploiter, it's a threat model, it's an attacker model. That doesn't seem to so bad. So the real reason why these vulnerabilities are so dangerous is because of the threat model over here that comes into play when you have network-facing programs. Okay, so just for a second, imagine that the program that you're talking about is a web browser that's actually vulnerable, not Firefox, not Google Chrome. These things are extensively vetted. But let's imagine that there's a buffer, there is a browser that you're using and it is vulnerable to a buffer overflow. There is a buffer overflow vulnerability in it. Okay, now your web browser almost by design is network facing because you're sending requests to arbitrary sites on the internet, getting back responses. The browser is supposed to read these responses, parse them, and maybe sort of display web pages, show a video or whatever it is, right? Now, if the attacker is sitting somewhere on the internet and they know that you are running this vulnerable web browser, they can send you an appropriately crafted set of packets that are then going to be read by your browser, which is then going to trigger this buffer overflow within the browser's code that's running in memory and exploit the buffer overflow vulnerability. So as a result, this remote attacker sitting somewhere on the internet has got complete control over your web browser, and as a result can do everything that your web browser can do. So for example, because your web browser can read the passwords that are stored in its own memory, the attacker can read the passwords that are stored in its own memory, okay, in that browser's memory. If there are any keys that are there or cookies that are there for active web browsing sessions, so maybe you're doing online banking, this remote attacker has got complete control over that. Okay, so you can get complete control. Hijack a program means the remote attacker has got the privileges of this program that he just exploited. Okay, so it gets even more dangerous than that. In fact, every computer system out there has got what are called secuid root programs. Okay, so I'm talking mostly about Unix style machines. There are equivalents in Windows as well. But what is a secuid root program? So a secuid root program is essentially, so what is secuid? So if you're not familiar with secuid, I suggest that you go and do a Google search for secuid. I'll just show you briefly how to go about doing something like that. Right. So here is my virtual machine. Right. So I do a man secuid. It gives you quite a bit of information about secuid. So it is actually in this particular case the command line utility, but it's a system call that is supported on most Unix systems that allows a program to set user identity. Okay, so remember I told you that when you start a process, you're actually starting the process. Let's say you are Alice, it's going to associate the privileges of Alice with this program. So secuid is actually an escape hatch or a particular feature on Linux that allows you to change the identity of the program that you're running. Okay, so why is something like this useful, right? So the reason that it is useful, I can probably motivate using an example. Okay, can you all see my screen, by the way? I'm actually in the virtual machine window.
Yes, sir, it is visible.
Yes, sir. Okay, all right. So how many of you are familiar with this program called password? You can actually see what it's used for, right? So it's used to change your password. Any Unix user can go and change their password using the password command. So I certainly did not mean to go and type my, okay, all right. So why is the password program, well, that's the functionality of the password program, right? So the password program is something that allows you to change your password. Where does the password program sit? Well, in my particular machine, it's sitting in /user/bin. Let me go and do password and see what it looks like. So you can see over here this particular tag that is associated with password. I'm looking at the permission bits. It says RWS R-X R-X. Okay. And I'll tell you what that S stands for, right? You might all be, if you have used Unix, you're familiar with the read, write, execute permissions, but there's this special bit over here called S, and that essentially indicates that password is a setuid program, okay? And you can see that the owner of this program is root, okay? Root 45250, whatever that is, okay? So what is this password program? Well, at the end of the day, it's just a binary program that's sitting on disk that I, as an end user, can execute. Okay. At this point, I'm executing as root, right? You can see that I'm logged in as root, but anybody can execute the password program, right? That's it's used to change password. So what is the password program's functionality? Well, where are passwords stored in your machine? Well, it actually turns out that passwords are never stored in the clear on your machine. That in fact, only a hash of your password is stored, and it's actually stored in this file called fcpassword. Okay, so you can see over here that there are various users, and it's actually talking about. So the password is not even shown over here. It tells you, which program to start as soon as you log in and so on. There's in fact another file called Shadow, where you store pretty much the same information, right? And what you can see is that some hash of the password is stored. The password is never stored the clear text. I can tell you the password of this particular virtual machine. The login is root and the password is root. In fact, you all have access to this virtual machine. Okay, so the password program, you can imagine that every time I go and invoke the password program and change my password, what is it supposed to do? Well, it's supposed to change my password. So it's supposed to go and write to this /etc/password file as well as the /etc/shadow file, right? So if I change my password, it's supposed to enter a hash of the new password into these files. Now, okay. So let me ask you this question. Who on a system should be given write privileges to the /etc/password and the /etc/shadow file? On a traditional Unix system that has many users, which user should be given write access or write privileges to these two files? Any answers?
To the root?
Your root. Why can't you give an arbitrary user permission to these files?
Because then they can tamper with other users' passwords?
Exactly. So anybody can go and change the password. So you should make sure that the only person who has write access to these two particular files is the root user. Okay. So we have concluded so far that the only user who should be able to write to these files is the root user. But think about it, right? So I am a regular user. In this particular case, I'm root, but let's for a minute, I have not created any other users. I don't want to create now. But let's for a minute assume that I am a non-root user. So what do I do when I am typing commands on the shell over here, right? So ls or whatever it is, what am I doing? Well, what I'm telling the shell is to go and fetch this corresponding program from wherever it's sitting on disk and execute it, right? So when I ask the shell to execute these programs are going to execute on my behalf with my privileges, okay? And that's exactly what happens when I run the password program, right? So if I have a user called Alice and I'm running the password program, I am asking the shell to execute this password program with my privileges. So if you believe what I just said, then this password program, when it started by this user Alice to change her password, is going to run with Alice's privileges. Okay, so the password program is going to run with Alice's privileges. Now we have got ourselves into a problem, right? The program is running with Alice's privileges. At the same time, it is supposed to go and write to the /etc/shadow and /etc/password, which are only supposed to be written by root. So how is the password program supposed to work? Right? It can't work because it's now running as Alice, or the process is running with Alice's privileges. So this is the exact problem that Ken Thompson and Dennis Ritchie, the inventors of Unix, foresaw. And this is the exact reason why they came up with this notion of setuid. Okay. So setuid allows a program to temporarily change its privileges. In this particular case, it allows the password program to temporarily change its privileges to root, even though it started off as Alice, go right to the etc password file and then downgrade privileges back to Alice. Okay. So this is a particular example of what is called a setuid root program, right? I mean, you can have setuid programs that allow you to change privileges from Alice to Bob, which is another user of the system. But a setuid root program allows you to temporarily elevate your privileges to root. Okay, so naturally, not any program is allowed to do this, right? And in order for a program to change itself to root, the root user has somehow got to bless this program or authorize this program and say, hey, this program, even if it started by user Alice, as it's running, it can go and change its privileges to root temporarily as it's running. And that's exactly what you see when you do the /user bin, what is that password? Right. So you see that it's actually owned by root. The program was installed by root. Anybody can invoke it. And this program runs with the privilege of the invoker. But the root user has blessed it in some sense by allowing it to be what is called a setuid root program. And you can do this with the chmod command. And because the root user sort of gave it the setuid privileges, which are indicated by this S bit in this in the permissions bit, the root user is saying, hey, I'm going to allow this program, even if it starts as a regular user, to temporarily elevate its privileges to root. Okay, so that's what a setuid root program is. So now, why did I tell you all this? Well, so I gave you the example of a web browser that's network facing. Now, imagine that you have a network daemon that is a setuid root program. So, in other words, it is a network facing program that is setuid root. Okay. So now what happens is that this program is network facing, which means that it is supposed to consume input that comes from the network, which means that an attacker can send an input and this program has been authorized by the root user to temporarily elevate its privileges to root. Okay, so now if the attacker can figure out the right sequence of commands, then the attacker is temporarily is able to sort of elevate his own privileges on the exploited machine to root. And once you have root privileges on the machine, you basically have complete access over the entire machine, which means that you can create new users, you can install new programs, you can wipe the file system. Nobody does that nowadays. You can install whatever programs, you can install ransomware. You can even go and reflash the operating system, right? The operating system actually executes at a higher privilege level than regular user programs. But the operating system files, they sit like other files on disk. You can go and reflash the operating system so that the next time the operating system starts, in fact, it is running malicious code that is given by the attacker. These are called rootkits, and we will see these examples of rootkits, and we will in fact see how to detect and prevent rootkits later on in the course. Okay, but that is sort of the ultimate goal of an attacker, to go and exploit and take complete control over a setuid root program. Okay. Any questions so far before I progress? No questions? Yeah, there are a few questions. Shubham, please go ahead. Shubham? Okay, I can't hear what he's saying. Shubham.
Sir?
Your voice is breaking up, but please start.
Sir, can any user, though all the user have execute permission for a password file, it means any user can change its own password without set UID root, right?
Yes, but if you change your own password, the password has to be written to the /etc password or /etc shadow file, which are both owned by root, and the only root has the permissions to write to those files. So that's why you need setuid.
Okay, it means I can't change my own password without set UID root.
Yes, because this program needs to be able to write to files that are
Yes.
only accessible to root. That's why you need SetUID root.
Okay. Thank you, sir.
Mahesh?
So the SBIT, what you have told, like which is available for some programs, whether that can be changed by root user, or like the root has the privilege to change that SID with the SBIT, or how it is set?
In particular case, the root user, in some sense, authorized this program to be a SetUID root program. So you as an end user cannot write a program with the SetUID system, call it, and then say, hey, I want this to be a SetUID root program. That program has to be explicitly given permissions by the root user with this SBIT to elevate its privileges to root. Otherwise, the command won't succeed.
Okay, so suppose if whatever I understand is correct, suppose if I'm a root user, so I can write a program and I say like I can set a bit SBIT to that program,
Yeah,
so that
correct. Yeah, so I would suggest that do a quick Google search of SetUID. In fact, do man SetUID on the virtual machine and learn about SetUID. It's a very, very interesting command. I have only exposed you to like one aspect of SetUID. It's a fairly expressive system call, and you have to spend some time with it. I have only exposed you to one aspect of it. Yeah. Gokula.
Sir, wouldn't be a better design decision to ask for a password whenever a user temporarily wants to change its privileges rather than using SetUID?
Ask for a password. What sort of a password, and where is this password stored, and who changes that password?
I mean, sir, that's some kind of password which the user might know so that it can escalate its privileges.
So, okay, let's think through this, right? So the user now, whenever they do something, you have to enter this password that allows you to temporarily escalate privileges. So that's what I'm asking, right? I'm talking about the bootstrap question. Who creates that password, and where is that password stored to elevate privileges? You're just pushing the problem down the road, right? You're kicking the can down the road. You have to now talk about how to change those permissions and how to change that password. That's not clear to me. Maybe you can explain your design in more detail. I don't understand that aspect.
So suppose so as you said, if Alice needs to access something, so suppose how it normally happens in our Unix systems is, suppose if I want to access a program which I don't have permissions for, I change my password I do sudo, and then I get into root, type a password, and then as a root user, I am able to access it.
Yes.
So wouldn't that be, so isn't that much safer than using SetUID and then allowing it temporary access?
Okay, so you just spoke about a program called sudo. Sudo itself is a SetUID program.
Oh.
Okay, here you go, right? Let's see. Oops. It's a SetUID root program, as you can see. Okay.
Okay, sir.
You can see. So, what you're talking about are methods, probably other alternative methods. But at the end of the day, when you boil down the problem to its core, you will find that you need a tool like SetUID. Right? Sudo is also a user space. It's a program, right? At the end of the day, it's changing privileges. How is it changing privileges? Because SetUID blessed it to do so, right? So what you're saying is absolutely right, but you invoked another program, sudo, but sudo relies on SetUID. So SetUID is the crux of the issue.
Yes, I understood, sir.
Okay. Yeah, Shashank, we will have to probably limit the number of questions. Always feel free to ask after class. I'll take as many as I can. Shashank, please go ahead.
Sir, this means that the program pass WD in middle of it somewhere escalates the privileges to the root. Correct?
Yes.
If I'm not wrong.
Yes.
Yeah. So if we have a physical access to a machine and suppose we don't have access to the root user, then can this program be, if we somehow alter the memory of this program in runtime, can we use this program to do anything as root?
Yes.
Okay. Yeah, matlab, is it possible, like in the current scenario, are there like defenses against this?
Yes, that's what the whole course is about. In October, you will see All right.
Yeah.
I mean, and it's not just physical access. That's the whole point of the course. That's the whole point of what I was trying to say.
Yes.
It's a network-facing program. Anybody on the
Yes, sir.
internet. Yeah.
Correct.
Yeah. Okay.
Correct.
Yeah.
Yes.
Okay. Yes, there are defenses. In fact, there are existing defenses that are deployed on your Linux system. You can go and do a quick Google search. We will come back and and talk about this later. It's called ASLR, or address-based randomization, and also what is called non-executable memory. So all of these things are coming up later in the course. Yeah. Aditya.
So can root essentially do a chmod plus s to set the setuid permission? So like how does root set that?
Correct.
Bit?
What you just said.
Okay.
What you just said, right? So chmod plus s actually gives you plus s or not. I don't know the exact syntax, perhaps I'm forgetting, but pretty much that way, right? I mean, chmod allows you to designate a particular program as setuid. Chmod or it should be chmod. Go do a man chmod.
I have the man page open. I don't see a plus s or something like that right now. So which is why I asked.
It must be setuid then. Go do a quick Google search, right? I mean, these are things that are best resolved using a Google search. I have not used these things in a long time, so my knowledge is rusty. But that's how you do it. You can do it using the command line, and you can essentially set privileges this way. So the root user is in some sense blessing the program, saying, hey, at runtime you can change privileges and copy. How exactly you do it, you can figure it out yourself. Right? Google is there to assist you with things that I don't know off the top of my head. Gaurish.
Sir, instead of using one shared file for all passwords, sir, can we use separate files for all users so that I only have to access my password file to change my password?
You can only. That's a good suggestion. I haven't thought that through. So at the end of the day, you can change your own password. It's not that simple. At the end of the day, you might want to give pseudo access to other people, and I'm not sure how that would work in that case. If you don't allow other people to go and change it. Actually, that's a good solution. I don't know why. I will have to think that through. Yeah.
Sir, I have 2 cents to share on this. Suppose we give access to the user, then he'll be able to directly access the file, which is not good in the interest of the user. Because a direct access to the file, I think, is not a good idea.
Yes, and you're right in the sense that what happens if this user's credentials themselves are compromised. But that's the attack. I mean, if that was the case, the same thing could happen to go and change their own password.
Like what if the user corrupts his own password file? Then he will be logged out. He'll be locked out of his own system.
But I can do that today. I can go and corrupt my own password using the password program, right? I mean, so the situation is no worse.
Yes.
But actually, what Gaurish is is a particular class of systems called egalitarian systems, where in some sense everybody has equal privileges, and there is no notion of root. We will talk about this, but this particular solution that you spoke about, Gaurish, I don't have like an immediate answer. Let me think this through of why that is not done. I'm sure there is a good reason, but yeah.
So while logging in, we have to set, we enter our password and the system checks our password. So in the Gaurish solution, the system will have to go into the user space of that particular user and then check the password is correct or not. While in our case, only the root can check if the password is correct. So will that pose an issue that you have to actually?
No, it doesn't pose an issue. It all sits in the file system, right? The file system is accessible to the login program. So that's not that's not probably the reason why. I will have to think of the right reason why, or figure out the right reason why this is not done. I can't think of the answer right now, so probably I'll have to get back to you on that. Yeah. Okay. Any further questions? Okay, so no further questions. Then what we can do is we can take it forward to the next. What is the next slide? There it is. Okay, yeah. Okay. So I think I already went over this, right? You have a get a space program and you have some really long content. What does it do? Well, it will more likely than not terminate with a segmentation fault. So the question is, what is a segmentation fault, right? I mean, I'm sure if you've programmed a Unix-like machine, you've seen these things. But do you really know what a segmentation fault is? Right? I mean, if you don't know, I would suggest that you Google it up and you actually Google up the origin of the term segmentation fault. Right? On chances are that you're working on a Intel machine or an AMD machine, or if you're on your phone, you're on an ARM-like machine. You are using Intel x86 64-bit or 32-bit, 64-bit more likely. The notion of segmentation doesn't exist, right? Segmentation is an older architecture. So, where does this term come from? It's actually an interesting historical concept. Go Google the origin of the term. But the idea is that, you get this, it's sort of a term that's used when you write to memory that you don't have privileges to write to. So you're probably writing to an unmapped page in your process virtual address space. I'll talk about virtual address spaces shortly. Or you're writing to, let's say, a kernel page, or you're writing to another page to which you do not have write access. And that's when you end up getting a segmentation fault. The hardware throws the fault caught by the OS, which then passes it to the program's signal handler if one exists. Otherwise, it just terminates the program's execution. Okay, so before we talk about the actual sites of the attack, we have to understand how the attackers locate these buffer overflow vulnerabilities in programs, especially when they don't have access to source code. So this, generally speaking, what attackers do is that they try to, when they get a new program and they want to see what, whether there are any problems in it, well, they can go and look at the machine code and try to figure things out. But more often than not, what they do is that they play with the program. They sort of try to interact with the program, feed it all sorts of garbage input, and then see what happens. Okay. So if the program crashes with a segmentation fault, that's not a good sign. That's generally a sign that there is a memory exploit, and then potential memory exploit, and then they go and dig deeper. Okay, with tools like GDB, which is a debugger, and objdump and so on, and then go try to figure out what's going wrong. Okay, so this way of interacting with programs is called fuzz testing or fuzzing, right? And it's a very popular methodology to test whether programs have problems. Okay, in fact, I would. This was so the notion of fuzzing is actually quite old. It goes back to the mid 80s, and so here is the web page of the person who invented fuzzing. Okay, back in 1988, as you can see, and you can see how fuzzing came to be. Nobody actually developed it because they wanted to develop fuzzing. In fact, this person he was working from home, as we all are right now. But in the back in the 1980s, when he was trying to sort of do a remote login to his server, he found that the network connection was not reliable because of a thunderstorm, and it was dropping packets. Okay, so even though he was typing meaningful commands on his command line, by the time it went and reached the server on which the commands were supposed to be executed, packets were dropped, whatever it is. So the packets reached the server in a slightly different form, and then as a result, what happened was that these programs on the server were crashing. Okay, so he didn't know what was going on, and then he dug deeper, and then he found that essentially garbage input was being fed to these programs sitting on the server, therefore causing the programs to crash, and thereby came the art and science of fuzzing. Okay, so for a long time it was known as a technique to make programs crash, but the only way to make programs crash was trying to feed it random input. Now, of course, it has become a science. You should all go and do this. In fact, I don't know if I'll be able to access it from within the IISc network. It's called AFL, or American Fuzzy Lob. It is a tool that's now developed by Google. There you go. That's the GitHub repository for AFL. It is the most advanced fuzzing tool out there, and it's used internally within Google as well as a number of companies that systematically generates random inputs to feed to a program. So you can run a program with AFL, right? For example, you can take your command line program, set UID or password or whatever it is, or you can even take a browser and run it with AFL. And AFL systematically figures out how to generate random inputs to feed to this program and explore many paths within the program and try to cause it to crash. Okay, so if it crashes, that's not a good sign. And if it passes without crashing, that's a good sign because it shows that at least the program doesn't have memory vulnerabilities. Okay, so it's a really mature program, AFL. In fact, over the last 4 or 5 years, AFL has really matured. And I told you that one of the things in this course that you can do is that, starting from essentially no background in computer security, you will go and reach like the cutting edge of a field. People worldwide are actively working on how to make AFL's search algorithms work better, develop new kinds of exploits and so on. So AFL is a tool that's right at the cutting edge of computer security in terms of defense tools or vulnerability and exploit discovery tools that allow you to go and systematically test programs. So AFL is one such program. And if you're interested, you should just go and take AFL. It's a very interesting program. Until 2 years ago when I checked, in fact, you could not even go and access AFL from the IISc network because it was considered a hacker tool, but I think now they have whitelisted it. So clearly I'm able to go there, or because it's probably GitHub. It used to be hosted at a different page and you could not go and visit it. Anyway, so that's fuzzing, and that's the tool that most users use as the first step to discover whether there are any vulnerabilities. And there are other methods too, source code inspection, machine code inspection, and so on. Okay, so now let's get into how these buffer overflow exploits work. So in order to do this, we need to understand how processes are laid out in memory, right? So in order to exploit a buffer overflow, which is basically, a problem in memory, you're trying to feed some garbage input into a program that's running. So what is a running program? Well, at the end of the day, it's a process, right? That's how things are organized by the operating system. So, what you see on the left of the slide is a program that's sitting on disk. When you run it, it becomes a process, right? So what is a process? Well, when you start a process, your operating system creates for it what is called a virtual address space, right? So what you see on the right-hand side of the slide is the memory representation of this process, or rather, I should be more precise, it is the virtual memory layout of a process, okay? So every process has an identical virtual memory layout. So every process looks the same in terms of the memory that's assigned to it, and this is all virtual memory, not physical memory, virtual memory. You can go and sort of understand this virtual memory layout. So the top of the picture here you see is top of memory. So I'll be working with 32-bit architectures because it's easier to write the addresses. They're much smaller. So the top of memory would be like the all bits 1 in a 32-bit address, and the bottom of memory is all bit 0. Okay. So in a 32-bit system, what is the size of virtual memory? Well, it is the size of the address space, right? So it's 2 power 32 or 4 gigabytes. Okay. So on a 32-bit system, you have 4 gigabytes of virtual memory. Every process has 4 gigabytes of virtual memory. This is mapped, of course, to the physical memory using the page table structure of the operating system. Okay. So right at the top of this virtual memory, you have the kernel code and data. So the kernel code and data are loaded into every process's address space. Okay, and below that somewhere you have the program stack, which is the activation record stack. Every time you invoke a function, that's where the activation records are pushed. Okay, that's right here. Then you have the heap, which goes upwards. Okay, and then the space for globals and the actual program's machine code. Okay, so this is how a process is laid out in memory. So it's important to remember that this is the top, this is the bottom, and then the stack grows downwards. Okay. Actually, can everybody see my mouse movements when I'm showing things? Because I'm using it as a proxy for. Okay, yes, good. Okay, yes. Good. Okay, so The code and data are sort of laid out that way, so the process data is all stored as an array of bytes, and the interpretation depends upon the instructions. Okay, so in C, C++, you can the code can directly access memory. There's no bounce checks. Okay, so it's vulnerable to buffer overflow exploits. Okay, yeah. So I've already spoken about the slide. Let me just see whether I've covered everything. Every process has an address space. The address space is a set of virtual addresses that are accessible to the process, and every address can store a piece of data, usually 1 byte long. So it is important to remember that this virtual address space, even though the entire virtual address space belongs to the process, not all memory here is addressable by the process. So the kernel memory, for example, cannot be written to by the process. So this portion over here, this code cannot write to this memory. Likewise, not all memory is mapped, right? So you have spare memory here that's not yet been allocated, and you go and try to read or write to it, you're going to get an error, a segmentation fault. And so that's the idea there, right? Every time you map memory, there is an entry that's created for you on the page table that then allows you to subsequently go and access that memory. Okay. All right. So these addresses are all stored as hexadecimal addresses. Okay. So on a 32-bit processor, the addresses will look like this. They will go from 0x00000000. That's hexadecimal notation, to 0xFF. Okay, so that's all ones. Okay, that's how memory is laid out. So the top 1 gigabyte is reserved for the kernel code and data. Okay, all right. So that's the process virtual memory layout. Okay, so every program, as it runs, it has some space allocated for it for something called a stack, which you all know. Every program has a stack. The stack is dynamic in the sense that it can grow and shrink as the program executes. So stack grows every time there is a function that is invoked, and it shrinks whenever the function returns. So I'll just throw out something here. It's sort of an interesting aside. So the model that I just spoke about works for single-threaded programs where you just have one stack. How do you think it works for multi-threaded programs? When you have multiple threads of execution, where do you think the stacks for the multiple functions sit? Any ideas? No? Well, Google it, right? So I'm not going to give you all the answers here, but that's something interesting to think about if you have not thought about it yet. But this is the model that we all study in undergraduate. When you take a course in computer organization, this is how you study it. But multi-threaded programs are all too common now. And when I ask somebody, where is the stack for a multi-threaded program? Generally, they don't know, right? So this sort of goes to show you the gap that exists between reality as it is implemented today and what is there in textbooks, right? So if you have never thought about the stack of a multi-threaded program, please go and do so today. Okay, but we'll be talking about single-threaded programs for the most part because it simplifies exposition, even though everything that I'm going to be talking about today works for multi-threaded programs as well. It's just that the stack sits somewhere else, right? It's not as shown in this picture. But there is the data structure of a stack, and everything that I'm going to talk about also applies to multi-threaded programs. Okay, so the stack entry reserves space for the function's local variables. That's basically the goal of having such a stack. If you have local variables, that's where you're allocated memory for the local variables. Okay, so the actual code for the program sits right here in the blue portion of this of the slide right here. That's where, you know, like this foo program with a getS with the char buffer that I showed you, that's where it sits. But at runtime, whenever that statement executing, you know, that char buff 1024, that memory, that 1024 bytes is actually allocated over here with the stack region. Okay. So let's look at an example of a program and its stack and see how things work. And what we will do over the next 20 minutes or so is that we will actually see how function call and return work. This is just a recap of what you have studied probably in a computer organization the class, but nevertheless, it's important because it is going to allow us to explore in detail what is there on the stack. Okay, so and that's important for understanding buffer overflow exploits. Okay, so let's look at a program with two functions. Over here, you have just got the main function and the foo function. Okay, and in fact, this is there in the virtual machine that you have with you. You can go and play around with it. So let's start off by assuming that the program has started execution as a process and that we are the main function. So over here shown in the blue or green or whatever that is, you have the main function and its corresponding activation record stack. We're not going to look deep inside this stack, but it exists. Okay, that's our setup right now when we are starting. And we have the stack entry for name. Okay, so now let's look at what happens when this function foo is called. Just for clarification, right? And this is going to be the bottom of the stack and it's going to be the top of the stack. Okay, so when you start executing this program, right? I mean, we have to sort of see what happens. So right, so just the stack grows downwards. Keep this fact in mind moving forwards. So Intel, right? It uses two special registers to keep track of the stack. Okay, I'm going to be using the notation for the 32-bit architecture, EBP, ESP. It's pretty much the same on a 64-bit architecture, except that the names of the registers are slightly different, right? It's called RBP and RSP, but the idea is going to be pretty much the same. Okay, but we'll talk about these registers over here. Okay, so all right. So when a new function is called, what happens is that a new stack entry is pushed to the top of the stack of the function foo. But several things actually happen before that. So what happens? Well, the argument in this particular case, the arguments just happen to be pushed in reverse order. So 3 is pushed, the literal 3, the bytes corresponding to the integer 3. We are talking about a 32-bit architecture. In this particular case, we are going to be talking about integers that are 4 bytes long. Okay, so the 4 bytes corresponding to the representation of the integer 3 gets pushed in memory. So ESP moves down by 4 bytes. 2 gets pushed in, 1 gets pushed in. That's exactly what happens when you call this function foo. And at that point, sorry, so that's what happens. So next slide, I will actually talk about how the assembly language happens. Okay. So arguments could be pushed by main or pushed by foo. This depends upon your compiler and how the code is generated, but that's pretty much what happens. Okay. So how do you find out what is happening? Well, in order to understand what is happening, you really need to go and look at assembly code. Okay, if you have never looked at assembly code, now is your chance to look at some assembly code. So let's go and look at this particular program sitting on our virtual machine. I hope I have this program. Yes, I think I do. It's called function call example. Is this the one? Yeah, that's the one. Okay, so here's your program. How do you compile your program? Well, you compile it using GCC. And when you compile your program, you get an a.out. That's the output. Okay. So let's go and look at our a.out. So how do you look at the assembly language? So this is the source code. How do you go and look at the assembly language? Right. One way to look at the assembly language is using a debugger. Right. You can actually go and look at the code of whatever is running using a debugger, but there are also other command line utilities available. And using one such utility, it's called objdump. Objdump -d a.out. It actually goes and lets you see the entire assembly code, the actual assembly code of the program. Oops, what happened here? Oh, there's no objdump here. Oh, there's a typo. Okay. So there's your assembly code for this program. It's pretty long, right? For a small program of probably 6 lines in length, there's quite a bit in assembly, right? This is the program. So this is not what executes on your machine. You have to pass this through an assembler, and it gives you the hexadecimal representation. But that's pretty much what executes, right? So you can see over here. This is how to read this stuff. So on the right-hand side, you can see all of the assembly language instructions, right? You see the, for example, I'm looking. Let's go and look at foo. Foo admin. Okay, so you can see the push EBP, move ESP, EBP, and so on, right? Those are the assembly language instructions. And let's look at the notation here. So 80483ED, right? What is that? Well, that's actually an address. That is an address of where this function is loaded in the process address space. Okay, so that's the 32-bit address at which this function foo is loaded in the process virtual address space. And the stuff that you see just after that at 8048ED, you see this 55. What is 55? Well, 55 is the hexadecimal representation of the push EBP instruction, right? Push EBP is human readable, right? You can read it, I can read it. It's low level, it's not at the level of C, but it's assembly. You can read it, I can read it. But 55 is the hexadecimal representation for the Intel x86 processor that understands that 55 is push EBP. So when it reads the 55, that byte 55, it actually knows that it has to do the push EBP instruction. Okay, so that's what that is. And what you can see is that even in this simple little example, right, where you have foo with a push, a move, a sub, a leave, and a ret, 5 instructions, on the left hand side, you can see that push is 55, move is 89 E5, sub is 83 EC20, and leave is C9 and ret is C3. Okay, so instructions are of variable length. Okay, this is a hallmark of Intel. The instructions come in variable length, and so sub with its 2 arguments, for example, over here, 0x20 and ESP is actually 3 bytes long. Okay, so that's how you go and view assembly. And if you look at this assembly, you can actually see what I just told you. Look at the lines in the main function. I'm not able to get my cursor inside the virtual machine for some reason. It's not showing up. But look at the 4th line of your main function. It, starting from the 4th line is exactly where the arguments are being pushed in reverse order, followed by the call instruction to foo. Okay, that's within main. Okay, so it's calling 80483ED foo. That's how the actual call is happening. Okay, so let's go back to the slides. Okay, so you will have to pick up a little bit of assembly. In fact, to do homework 1, you will have to pick up some assembly, and I trust you all to do that. So here's a very quick tutorial of x86. Probably most of the instructions that you will encounter for the purpose of doing this homework. But of course, the x86 manual is much more complicated than this. If you go and look at the x86 manual, it's around, it's a book it's 2 books, each around 3 inches thick. Okay, so half a foot tall. And so what I'm doing here is probably just looking at the surface over here, the bare minimum of what you need. So push L is an instruction that actually pushes something on the stack. In this particular case, it's pushing the contents of the register EBP on the stack. That's what that instruction does. And I'm just exposing these to you because we'll be seeing these instructions in the next few slides. As you can see, I'll just give you a preview of what's coming up. You will have to learn how to read some assembly. So let's go there, and you will see that you will have to read some assembly. Oh, here you go. There's a slide full of assembly code. So we'll have to understand how this works. So we will have to learn a little bit of assembly. So let's learn that, going back to where we came from. Okay, so push is going to push something onto the stack. Move L, ESP, EBP. Okay, so as I told you, assembly language is human readable, and it just so turns out that there are 2 different notations for assembly. One is called the AT&T syntax, one is called the Intel syntax. And it just so happens that the AT&T and the Intel syntax use exactly the opposite convention for source and destination. So I don't know what syntax I'm using. God knows what these names are, but let's stick with the syntax that we are using. So move L ESP EBP means that you're moving the current value of ESP to EBP. Okay, if you use a different disassembler, or if you were to use a slightly different, the other notation, the source and the destination will be reversed. Okay, so you have to figure out what assembly code you're using and then read it that way. But in this particular case, ESP is the source, the first one is the source, the second one is the destination. Okay, in case I forget, remind me. I usually confuse myself, but that's why I have this slide. Okay, so sub L is just subtract. It's subtracting a value of 4 from ESP. Call is a very interesting instruction. It is, you can call with an address. The name of the function really doesn't make sense to the processor. You have to specify the address. Okay, so this calling the function at that address, and we will see a little bit more about what this call instruction does. So obviously the call instruction has to change the instruction pointer to go start executing from this address, but it also does one other thing that's going to be very interesting for us. It pushes the return address onto the stack. Okay, so at a call instruction, what's the return address? So when I call that function, what is the return address? Where should you return to after that function is
The
completed?
current instruction pointer?
Well, the next instruction, right? I mean, the instruction just following this call. That's exactly where you should return to, because that's when you've finished the call and then you should resume from there. So the instruction just following this call, that is the address that's pushed onto the stack. And if you want to go and look at our example over here, you've got a call. So if you see this call instruction in the main program, the return address will be the address 8048417, because that is where you should return to after the call is completed. Okay. So the reason you have to do this is because this function foo can be called from multiple places, and the processor at any given point in time has to know after the function foo is completed where it should return to, right? And that's the return address. That's what is going to be stored on the stack, and we'll see that this is the most important aspect of buffer overflow exploits. The fact that this return address is actually stored on the stack. Okay. Okay. Moving on. Literally speaking, right? We've got now the move instruction. So the move L instruction over here, it's actually moving a value 1, but what I want you to pay attention to is this particular notation over here. EBP, which is a register name followed by some offset over here. Okay, so what this offset over here is that it's actually EBP plus this value. Okay, EBP plus this value. EBP it's a register, it can store any 4-byte value. And in this particular case, EBP, let's say it's storing an address in memory. It's going to add this particular offset to that address. And what is this number over here? Well, it's all 2's complement arithmetic. Okay, so it's actually -4. So EBP -4, EBP is an address, you subtract 4 from it. That is also an address. And what this instruction is saying is I'm going to store the value 1 at that particular memory location. Okay, so if you are familiar with C, it is like saying star P equal to 1, where P is the pointer, right? And the pointer is the value of whatever is stored in EBP -4. Okay, let's move. LEAL, it stands for load effective address. Sorry, there's a question. Was there a question? Okay. So LEAL is just a load effective address. And what this does is that it loads the address of the memory location pointed to by EBP -4. So EBP -4, whatever memory address that points to, it's going to be loaded into EAX. So LEAL, in fact, you can implement LEAL with move as well, but you'll see that there's a lot of redundancy in the Intel x86 architecture in terms of instruction set. And in fact, you will see that attackers have put this redundancy to good use. We will talk about this as well. Okay, so the ret instruction is an important instruction. It returns. What it does is that it pops off the return address and returns to the address that is saved on the stack. And the NOP is the no op instruction. Okay, so let me see how far I can go. I have another 10 minutes, and probably what I will do is I don't want to stop at some intermediate location. So let me just carry on and stop at a logical point, and we'll start off the next class from there. Okay, so I'll go until slide 40. I think that's a reasonable stopping point. Okay, so let's look at the program into functions, right? So the arguments are pushed in reverse order. That's where we got. Now, why is it pushed in reverse order? Well, it can be pushed in any order, but it just so happens that in this particular case, the compiler that I used pushed the arguments in reverse order, and you can sort of see this over here, right? And we already saw that the move instructions were sort of pushing these things in reverse order. The only thing is that the compiler is aware of the entire program, and as long as it's using the same convention throughout, you can push in any order. Okay. All right. So, okay. So We have already seen this, so let's see. I'm pointing to an instruction: move L 0x3 ESP plus 8. What is this doing? Well, let's go and look at the assembly where this thing was there. So where I just moved down. Oops. Yeah. Oops. There you go. So you can see the first instruction: move L 0x3 0x8 ESP. You know, what is this doing, right? I mean, if you think about it, it's just storing the value 3 at ESP plus 8. And that sort of goes to show you how things are stored on the stack. Whatever is the current value of ESP, add 8 to it and store the value 3 there, right? That's what it's doing. You could also do a push, and that's fine, right? In which case, it's going to store the value 3. The push has the implicit side effect of also changing the value of ESP. Depends on the compiler, whatever is used. Okay. Finally, the call instruction that I was talking about, right? ESP gets pushed down. The return address is pushed onto the stack. The return address in this particular program will be the instruction immediately following foo. It's nothing. It's an implicit return. But in any case, right, if there was more code following this foo call over here, that is the address that would be pushed onto the stack. Okay, so when you call a function, the processor needs to remember where to return to, and that is the return address that's stored on the stack. Okay, and in this particular case, I already went over the code. I told you what the return address is. If you look at the code, it will be 8048417. The instruction just following that foo in that virtual machine that we were looking at. Okay, you also see that. Okay, so now what we'll do is we have finished with foo. We have finished with the body of main. We will now go to foo and look at the assembly code for foo. So the first thing that you can see what happens within foo is that it's doing a push of EBP. Okay, so let's go back to our slides over here. So what do you think it is push EBP? What does push EBP do? Well, it stores the current value of EBP on the stack. Okay, so you're saving the value of EBP on the stack, and you will see that the next instruction in foo is that it's moving ESP to EBP. Okay, and it's subtracting 20 from ESP. Okay, so what's going on? So what it's doing is that it's moving EBP to ESP, which means that now EBP and ESP are going to be the same value, and it's subtracting 20 from ESP, which means that ESP is now sort of it's 20 hexadecimal. Okay, so it's 32 bytes, but it's subtracting some value, so ESP has now come down. Okay, so now this sort of should give you the hint for why you saved the value of EBP, because this function foo, once it returns, you should know how to restore the value of EBP. Right, EBP is currently pointing right here, and when the function foo returns, EBP needs to point over here, right? So where do you get that value from? You need to have saved it somewhere, right? ESP will point to where after this function returns? Well, it will point to over here, which you can calculate with from the current location, right? Wherever EBP is minus these many bytes will give you ESP. So you can calculate the new value of ESP from EBP after the end of the function, but how do you know what EBP is? You don't know, right? That's why you saved it here, right? You saved the value of EBP so that you can just read it on the stack and then restore the value of EBP. EBP is also called the frame pointer. EBP is called the frame pointer. ESP is called the stack pointer. Okay, so at any given point in time, you want to maintain the invariant that EBP is pointing to the bottom of the current stack frame, and ESP is pointing to the top of the current stack frame. And that is the invariant that is being maintained by saving this value of the EBP on the stack. Okay, and in this particular case, right, foo has got two local buffers, buff1 and buff2, 8 bytes and 12 bytes, but the compiler can give more or less, and they are laid out on the stack. Again, how they are laid out depends on the compiler. In this particular case, I'm drawing buff2 above and buff1 below. It could be the reverse, doesn't matter, right? So it stores the space for these two buffers, 12 bytes and 8 bytes on the stack over here. Okay, so why save EBP? I already went over that. So I think this is a good time to stop the class, because at this point, what we will do is that, remind me, I stopped at slide 40. This is the setup that we will begin with tomorrow, on Monday. And what I will do is I will show you how from here on you can actually go and overwrite the return address, and an attacker, let's say, there is a gettr statement in this program, get s into this buffer. You can actually write into this buffer and overwrite the return address and then make it point to any value of your choice. And that's how the attacker is going to take over the program. Okay, so I will go over the entire steps of how that is done in the next class. In fact, what I will show you is how you can overwrite the return address to spawn a shell with the privileges of this particular program. Okay, so that's where we are going at on Monday. Start at slide 40. Please remind me in case I forget. Next class we will continue. Any quick questions before we stop the class? Yes, Aman.
Yes, sir. Why 32 bytes are allocated?
Why 32 is it? Yeah, that depends on the compiler, right? The compiler might decide to do things along word boundaries, page boundaries, whatever it is. That depends entirely on the compiler. There might be other local variables. This is not something that we have control over. If you look at the assembly code, you'll know exactly how much is allocated. Okay, it's entirely compiler dependent.
Okay, thank you, sir.
Any other questions? Okay, so let us stop the class for now. And wait, somebody else got unmuted. Okay, let's stop the class and we'll continue from slide 41 in the next class.